Hi, everybody. Oh, it's loud. So I'm going to talk about the hydrology and climatology monitoring that's been done in the oil sands, and specifically about a water balance approach that we use to try to identify and quantify effects of oil sands development in the region. And so, as an overview, the purpose of the program is to monitor hydrology and climatology in the oil sands region, and then to try to identify and quantify the changes in hydrology. I'm going to talk a bit about the data collection that's been done to date, and then I'll get into our water balance methodology and then some results. The JOSM Hydrology and Climatology program is composed of data that's being collected by Water Survey of Canada, Environment Canada, Alberta Sustainable Resource Development, and Hatfield. There's some other groups that are also collecting data, but not maybe specifically, but more kind of at random. In the last year, we ran, or as a group, we ran about 57 hydrometric stations, 6 lake stations, 11 comprehensive climate stations, and 7 additional stations that collected precipitation and a few other climate variables. As far as data availability goes, the climate data collection started in the 1940s at Fort McMurray, and then in the 1990s it really started to pick up with Environment Canada establishing the Mildred Lake site, and then RAMP establishing Aurora, and now we're at 11 stations in the area. And as far as hydrology goes, the monitoring really began in earnest in the 1930s with monitoring on the Athabasca and Clearwater, and it's picked up since then, and we're now at a point where we have at least 30 years of data for pretty much all the major watersheds that contribute to the Athabasca in the oil sands region. There's a fair bit of collaboration and data sharing that goes on between the groups. We use hydrometric data from 10 Water Survey of Canada stations every year for our annual reporting. RAMP, starting in 2000, started collecting data in the winter time at some of the Water Survey of Canada stations that weren't operated in the winter time to allow for continuous year-round records, and that in 2013 was up at 7 stations that we did that at. And over the years also, RAMP reestablished monitoring at 10 stations that were discontinued by Water Survey of Canada to try to take advantage of the historical records that were there and try to extend that record as much as possible. And all the data that we collect is available on the JOSM database. To get into the water balance approach, it's based on a hydrograph that's measured near the mouth of a watershed. And what we really try to do is back calculate a baseline. We know that what we measure or what's observed today has some type of impact on it, or has some change. So we try to quantify the different components that are affected, and then to calculate it in. So we receive data from industry about their water withdrawals and releases, and then we either remove those out if they were released, or put them back in if they were withdrawn. And then we make assumptions, or we have assumptions made on the closed-circuited areas, hydrologically closed-circuit areas such as a tailings pond, for example, or a mine pit, which we assume doesn't produce water to the runoff. And so we add those areas back in, and if the area has been cleared by industry, we subtract a proportion of the water for these areas because of the runoff characteristics. And we do this on a daily basis for every day of the year. And then we compare the calculated baseline hydrograph to the observed, and come up with an assessment of change. The assumptions that we use is, at this point, we don't include groundwater in the water balance. We also don't consider timing or lag within the water withdrawals, releases, or delays from the the cleared areas, for example. So pretty much if we have data that occurred on any given date, we assume it occurs on that same date at the mouth of the watershed. The cleared areas, we're making the assumption that they produce an additional 20% runoff in the region. That's based on the Spring Creek study. And the closed circuit areas don't contribute to the surface water system. We assess the water balance based on 4 measurement endpoints. So the mean open water season, mean winter and annual maximum daily, and the open water season minimums, and the date ranges are given there. And we use effects criteria where we judge how big the change or the impact is based on criteria that were developed or were derived from regional ERAs, and we consider negligible low at anything below 5%, moderate at between 5 and 15%, and high at everything above 15%. And those dots are a little bit off. Basically, they're a color code. Yellow represents negligible low, the orange represents moderate, and the brown is a high, and you'll see that coming later in the results. Sorry about that. The closed circuited and cleared areas are developed using a land change analysis, and what we use is a 5-meter resolution multispectral images, and we analyze those to assess land change or detect land change, really. The image acquisition is usually done in the summertime. We need clear cloud conditions, so it's usually sometime between July and September, whenever we can get it. And then we calculate the land change. We take the land change back to industry folks and then help them, or they help us identify or nail down what is closed circuited and what is not. And when I mean closed circuited, it's really the areas that where water is not allowed to enter the natural system anymore. So an obvious example would be a tailings pond. And so to get into some results, I've chosen a couple of watersheds of interest. The Muskeg River watershed is one of the more dynamic ones. It has a little bit of mix of everything. So the map on your left shows with the green areas is what we've assessed as the closed-circuited areas. The yellow areas is the cleared areas. And if you squint, you can probably tell some black dots, which are our withdrawal and releases. And so when we run the water balance, we create these 2 hydrographs, so where we compare the 2 hydrographs. The observed is the red line in the graph on your right, and the calculated natural or calculated baseline is the gray dotted. And I've just pointed out there that the peak maximum or the maximum daily discharge decreased in 2013 by about 7%. So had the development not been there, it would be about 7%, or estimated to be about 7% higher. Oops, wrong button. And if we look at the 4 measurement endpoints, the annual maximum, as we talked about, was 7% decrease. The mean winter discharge was a decrease of barely a percent, or not even a percent. The mean open water, 6%, and the minimum open water was an increase of 15%. The Athabasca River watershed is a bit, it doesn't have the most interesting results, but I think it's valuable to note. And the map is, what it's trying to show is just the scale of the watershed relative to the actual development area. The development is up in the northeast of the watershed, and it's quite small relative to the to the size of the watershed. So the effects that we do see are generally quite small, just because of the amount of water and the relative size of everything. So when you look at the hydrograph, the observed versus the naturalized is very difficult to actually see a difference. And when we look at the results, they're all within about a percent for all 4 measurement endpoints. And when we look at the whole region of the whole oil sands, all the watersheds, we sort of see the pattern with the muskeg being kind of one of the only ones which has a little bit more variability in how the effects are happening. But on the larger watersheds, such as the Steep Bank, the Ells, the Mackay, and a few others, there is really very little change that's detected based on the size of the size of the watershed and the amount of development, versus some of the smaller watersheds such as the Tar or the Mills Creek, Fort Creek, Poplar. The effects are quite high just because of the size and just the amount of development. And to get into some future considerations, so the water balance approach it's not the fanciest, it's not, maybe it doesn't give us the best examples or most clearest answers, but it has a lot of value in that there is essentially no historical data that's required to run this water balance. You can set up a monitoring station, and in the next year you can start to assess change. Talking kind of from a bigger scale, I think groundwater would be a valuable piece to be able to add in to get a more comprehensive idea of what's happening in these watersheds. And just like to say thank you, and acknowledgements to AEMERA for hosting this event and allowing us to speak here, and then the oil sands operators for putting up with our pestering for data, and to Water Survey and Dennis for always being good about providing data for us as well.
Thank you. So we do have a couple minutes for questions. Are there any questions then on the water withdrawal, surface water? Okay, great. I did like the fact that after the presentations, oh, there's one. Okay.
Question: what's the uncertainty around those estimates?
Well, realistically, the hydrograph, you're not going to get it down below 5%. So, and that's why negligible low is considered 5%. So that kind of has that's sort of what we've always assessed it at, is plus minus 5%.